Okay, Samuel?
We are the Genesis generators, and this is our project on flight delay prediction. We made this project because a delayed flight can cause a last-minute shift in schedule and unneeded time in an airport, which is every flyer's worst nightmare. In order to prevent flyers from having to deal with this inconvenience, our team developed a model which can show users if there will be a delay. Both airport companies and flyers will be able to use this model to adjust their schedules accordingly. So for the first week, we did exploratory data analysis in order to find a reliable database. In the second week, we did machine learning. We trained the AI and added parameters. And in the third week, we deployed this website.
So for the exploratory data analysis process of our project, basically before predicting any delay behaviors, we needed to establish an understanding of the data we were working with and also find correlations between the different features that we were looking at, such as the airlines being traveled or the length of the flight and the flight being delayed, and also to identify what these correlations mean. And so we also use the airline delay prediction data set on Kaggle for this project. And so if we look at the plots below, first we have the heat map, and this basically displays the correlation between each of the features in our data set that I talked about earlier. And since there's a low correlation between the numeric value variables and target variables, we tried many different transformations on the data to achieve the best results. And then if we go to the airlines data, basically this is a bar graph that shows the amount of delayed flights compared to the on-time flights per airline. And so the red bar represents the flights that are delayed, and the blue bar represents the flights that are on time. And in the graph, you can see that the ratio between the flights delayed and flights on time are pretty similar, except for the one airline, which is WN, the one on the far left, which is Southwest. And Southwest has almost double the amount of delays than on-time flights, and it also has double the amount of total flights compared to the second most common airline, which was DL. And then if we look at day of flight, we can see that it's the same concept where the red represents the delayed flights and the blue represents the on-time flights. And you can see that the middle of the week was the busiest times for all flights. So Tuesday, Wednesday, and Thursday, specifically Wednesday the most, and Friday had the least amount of flights. And then if we go to source airports, this is basically a bar graph that shows what airport each flight flew from and if there was a delay or not. And so basically you can see that on the left, there's a large amount of flights, and then on the right there's a very small amount, and this just means that on the left side, the large amount, we had a lot of data from that specific airport, but for the right side we didn't really have that much data, so we just put that into the other category so it doesn't affect our predictions. And then if we go to the final one, which is destination airports, this is basically the same concept of the last graph, but instead it's basically the destination, so where the airplane is flying to. And the busiest airports as seen in the graph are ATL, DEN, and Phoenix, and there are usually more on-time flights than delays. And so the rest are just box plots, and you can see that they're the arrival times, whether the flights were delayed or on time, and the flight duration to see the delay or on time, and it basically just showed the distribution and the variation, so we could also take that into accountability when we were looking at the predictions.
After completing our EDA, we now know how to clean our data. A few examples of how we transformed our data include dropping the rows where the flight duration was 0. This meant that the flight length wasn't recorded, so including these rows would mess up our results. We also dropped unnecessary columns, such as the ID column. The ID column just numbered each row in our data set, so we didn't need that column. Then we also encoded categorical variables, such as the different airport names and airlines, into numbers. Since our model can't understand strings, we had to change them into numbers. we also cut down a large sample size of 500,000 to random sample of 5,000 for data visualization and 20,000 for training and testing the model. But computers can't handle the large amount of data, so cutting down our sample size helped our processing speed. We also cut down the number of categories in airport to and airport from by grouping any airport with 3 or less samples into another category, as mentioned before. And now Aanchal will talk about our machine learning.
Thank you, Justin. So now I will, now I will again give you an introduction to the baseline machine learning models we used in our first iteration of these classifications models. So we started with the k-nearest neighbors, support vector machines, Gaussian naive Bayes, logistic regression, gradient boosting, random forest, and decision tree algorithms. And from there, we chose 3 different models to develop further based on their baseline performance, meaning their performance without us setting any hyperparameters. And we judge this by some chosen performance metrics we'll get over in a little bit. And then also I will go over the details of the models we ended up choosing below. One note about the hyperparameter, the fact that we didn't set any hyperparameters, we did include some things to give each model a fair shot, such as giving the SVM a polykernel, so that way it can give a slightly more accurate classification. So the metrics we used for choosing a baseline model, we prioritized the precision, which is the false positive rate, since we wanted to minimize the chance of the model thinking that there is, or predicting that there is a delay, which is a positive prediction, when there actually isn't, which is a false prediction, since this would end up with the worst case scenario of the flyer being linked to the flight. Of course, we also kept in mind other performance metrics, such as accuracy. So we ended up picking our top 3 baseline models were Gaussian naive Bayes, gradient boosting, and random forest. Later on, again, I'll go over the performance metrics and what those meant. But first, I'll talk about the details of these 3 models. So Gaussian naive Bayes essentially predicts, this is going to be very technical, and I don't expect anyone to understand this completely, but essentially what it does is it predicts the probability that a certain data point will belong to a certain class, and then the class with the highest probability is chosen. And this model specifically is different to other algorithms in that it assumes each feature is independent of each other, like each input doesn't have any ties together. And this model is most efficient with a small sample size and also categorical features. However, some cons of this is that even though that it seems that taking each variable as independent is a good thing, it can actually be a bad thing since features in real life actually do have an impact on each other. The next 2 models I'll go over are both ensemble methods. Gradient boosting is an ensemble method that uses a collection of weak decision trees to build a strong model. And then each new tree uses information from the previous iteration tree to improve. And because these trees are built to correct the previous one errors, gradient boosting is able to pick up complex patterns. However, it is also more susceptible to noise in the data because of this, so you have to be really thorough in your data cleaning. Random forest is another ensemble method that also operates similarly to gradient boosting in that it generates multiple trees. However, instead of using information from previous trees to build the next, they make a bunch of, random forest makes a bunch of trees that are independent of each other, which helps the model as it is less susceptible to picking up any noise, but it loses to gradient boosting in terms of picking up complex trends. So now the evaluation of the baseline models, so just again without any hyperparameters that we had set. Again, the 3 best models were Gaussian naive Bayes, gradient boosting, and random forest. The gradient boosting model had an accuracy of 0.67 and a precision of 0.66. The random forest model had an accuracy of 0.65 and a precision of 0.62, and Gaussian naive Bayes had an accuracy of 0.63 and a precision of 0.59. And below we have confusion matrices showing the actual predicted values for each model, along with a bar chart depicting the precision and accuracy for each model, which is what I just told you about. And since the accuracies for each model were pretty similar, we could safely use precision as our sole qualifying metric for moving those models onto hyperparameter tuning. And Ayesha will now talk more about the hyperparameter tuning process.
So after our first iteration of training our machine learning models, we wanted to see if we could improve their precision. So basically, we decided to focus on precision because we wanted to reduce the number of false positives we were getting. So we chose a bunch of different values for the hyperparameters for all of our different models. And we use sklearn's grid search class in order to automate the process of training, testing, and evaluating all of these models using precision as a metric to figure out which models and which hyperparameters were the most effective. Let's take a look at the results of the tuning process. So we are only looking at the top 3 models, gradient boosting, random forest, and Gaussian naive Bayes. And we can see from the confusion matrix that the number of false positives is very low on all of these models. And that's a good thing because it means that our process of hyperparameter tuning did work. So on the top right, we can see these are the false positives, and it's pretty low for all of the models. And then this graph shows other metrics as well for evaluating classification models. We've seen accuracy and received precision, but it also shows the recall and the F1 score, which was explained before as a weighted calculation of the precision and the recall. So overall, it seems like gradient boosting had a really good precision and a highest accuracy out of all of the 3 models that we decided to evaluate, but the recall is pretty low. But all of these performed pretty well, and the hyperparameter tuning did help to improve their performance. And now I just want to quickly demo how this would work. Our prediction is very primitive right now. It doesn't look pretty with all the CSS. We have just HTML, so it's a plain form, but we just wanted to show you how it works. So basically, it's going to take us to this very fancy website, and we can type in some numerical value. So this needs work. It wasn't part of our MVP, but we still wanted to show you guys how this works. So I'm just going to enter in some numeric data, and then we can see what this model predicts based off of these arbitrary values that I'm typing in. The model predicted that there is not going to be a delay when we put in all of those specific values. Okay. Now I will hand it back to Sarah to conclude this presentation.
Okay, thank you. So from the first few iterations of our model, we can figure out what changes need to be made in the future. Firstly, we can perform feature engineering on our 2 highly important variables, arrival time and the airline. Feature engineering includes numerical manipulations such as adding or multiplying the features together. We can also look to increase our processing power so that we are able to utilize the full dataset or using an entirely different dataset, which includes a greater variety of features. Despite the subpar performance of the model, we have built a strong foundation for future research. We have found trends in the data and developed a model that, if used with a higher correlated data, could become more accurate. And here's our team. It's Ayesha, Aanchal, Justin, me, Sarah, Sanjana, and Samuel. Thank you, and any questions?